Welcome to the Mathematics of Thinking. In this playlist, we'll be diving into famous variety of algorithms. We'll be breaking them down into visuals and in order to understand how they empower every tool we use every single day as a data engineer. So yeah, let's get started. Today we'll be talking about Markov chains. This is the model behind Google's original PageRank algorithm. It is the foundation underneath large language models, and it explains how your phone predicts the next word you are about to type. One simple idea, enormous consequences. Imagine yourself trapped in this situation. The world is random. You cannot know for certain what happens next. The stock market, the weather, what a word a user types next, what page a visitor clicks to. But there is the thing, pure randomness is rare. Patterns exist. What happens next usually depends on what is happening now. So it's sunny today, so it's more likely to be sunny tomorrow than rainy. If a user is on a product page, they are more likely to go to checkout than back to the home page. So the question becomes, can you build a model that captures these transitions probabilities and use it to simulate, predict, and reason about sequences? Yes. And the model is called a Markov chain. The same model that Google built its entry search ranking on. The same model that underlies how LLMs generate text, and it all starts with one elegant property. So what is a Markov chain? The concept, so let me break it down to you. So we have states. It's a finite set of conditions that system can be in our example, sunny, cloudy, rainy. In Google's case, for example, it's every page on the internet. In an LLM, every token in the vocabulary. Transitions, then we have the transitions, the probabilities of moving from one state to another. If we are in the sunny state, there is 17% chance we stay sunny, 13% we move to cloudy, and 0 chance we jump straight to rainy. Crucially, all probabilities leaving a state must sum to 1. You always end up somewhere, more or less. This is the Markov property, and it's the most important concept. The future depends only on the present state, not on how you got. Not on how you got. Here, not on yesterday, not on the last week. So it's sunny today. The probability of rain tomorrow. It's the same whether yesterday was also sunny or whether it has been raining for a week straight. So look at the diagram in the bottom. That's our weather chain, like built with the Markov chain. We have 3 states, transitions between them. Each node loops back to itself with a self-transition probability. We have the transition matrix. This is how we represent all of this mathematically. So it's a square matrix where row I column G equals to the probability of going from state I to state G. Okay, look at the right panel. That is our weather matrix. Row sunny, 0.7 stay sunny, 0.3 go cloudy, and 0.0 go rainy. Row cloudy, 0.3 go sunny, 0.3 stay cloudy, 0.4 go rainy. Row rainy, we have 0.2 go sunny, 0.4 go cloudy, and you have 0.4 stay rainy. Every row sums to 1 always, because the sum of probabilities is always 100%, which is 1. Now here is where the math gets powerful. So if you raise this matrix to the power of n, matrix multiplication n times, you get the probability of transitioning from state I to state G in exactly n steps. And as n approaches the infinity, so it's like counting the limit, as you multiply the matrix by itself enough times, it converges to a fixed distribution. Every row becomes the same vector. That vector is called the stationary distribution. It tells you in the long run how much time the system spends in each state, and the convergence, that is exactly how PageRank works. Okay, so PageRank, let me show you how Google built its entire search algorithm on this idea. The model is called the random surfer. Imagine a person surfing in the internet at random. They are on a page, they click on a random link, they land somewhere, they click another random link, and so on forever. The web is directed graph. Pages are states, links are transitions. Every link on a page has equal probability. If a page has 4 links, each link has a 25% chance of being clicked. Now the question is, where does the random surfer spend most of their time? Which page does the random surfer visit most often? So the answer is the stationary distribution of the web's Markov chain, and the distribution is a PageRank score. Look at the right panel. We have 4 pages. Page A has a rank of 0.38. Page B has 0.12, not because of the content, but because of the structure of links pointing to each page. We have the page A has the most inbound links. The random surfer visits it most often, so it ranks first in the search results. Brilliant, and it's all just a Markov chain converging to a stationary distribution. Now, the one that most people do not connect is how Markov chains relate to language models. So let us just start a simple question, or like a background model, like starting simple. A background model is the most basic language model. Given the last word you type, what is the most likely next word? Okay, that is a Markov chain. States are words in this case, and transitions are learned from training text. An n-gram model extends this to n words of context, still Markov, just a higher order version. Then came the transformers. We have GPT, Claude, Gemini. These use attention to look to at all previous tokens, not just a fixed window. So technically they are not Markov in the strict sense, but here is what stays Markov at every single step. The output is still a probability distribution over the vocabulary. The model produces a vector of probabilities, one per token, and you sample from it. Okay, so look at the right panel again in here in this page. Context, the data pipeline. The models assigns 32% to failed, 28% to runs, and 18% to crashed, and so on. You sample from the distribution. Failed is chosen. The output becomes the data pipeline failed. Next step, same process. Now the context includes failed, and new probabilities are computed. So token by token, step by step, a Markov style transition at every generation step. The sampling strategy, temperature, top K, top P, control how you sample from the distribution. Low temperature makes the model determinist, always picking the highest probability. High temperature makes it more creative in sampling from further down the distribution. So here is the implementation, 3 things in one file. First, the transition matrix, a nested dictionary. Outer key is the current state. Inner dex maps next states to probabilities. This is the most readable representation for small chains. Second, this simulate function. We start at a given state. At each step, we call random dot choices with the transition probabilities as weight. Python's random dot chase handles weighted sampling natively. We call X the path. And third, we have the stationary function. So here we run a very long simulation, 10,000 steps. At each step we count how often we visit each state. At the end we normalize the counts by the total. So as the number of steps grows, this converges to this true stationary distribution for our weather chain. You should get approximately like sunny around 43%, cloudy around 36%, and rainy around 21%. Let me show you where this appears in the systems you already work with. We have Google PageRank, we covered this, the entire original search algorithm, the web as a Markov chain, stationary distribution as ranking. We have the LLM token generation. Every token step is a weighted sample from the vocabulary distribution, Markov at its core. Autocomplete on your phone. Your keyboard uses an n-gram model trained on your typing history. It is literally a Markov chain personalized to how you write. Finance and risk modeling. Speech recognition using a hidden Markov models. This is where things get deeper. In an HMM, there are hidden states, the true phenomenon being spoken and observed states. The audio features, you cannot directly observe the phenomenon, only the sound. The model infers the hidden sequence. That is what powers the classical speech recognition. And reinforcement learning. Markov decision process are the foundation of every RL algorithm ever built. DQN, PPO, the algorithm behind AlphaGo, the RLHF training of ChatGPT, all MDPs, all Markov. Now, as usual, we have two numbers, space O of S squared. S is the number of states. The transition matrix has one entry per state pair with then 1000 states, which is small for real applications. You have 100 million entries. This gets large fast. Time O of S squared times N for N step simulation via matrix multiplication, sparse representations and approximations become necessary at scale. We have three limits to understand for this algorithm. First of all, the memoryless assumption. The Markov property says only the current state matters. If your real system depends on history, like a user's browsing session or a time series with trends, a first order Markov chain is not enough. You need higher order models or recurrent networks or transformers. Second, state space explosion. As states grow, the matrix grows quadratically. Real language models cannot store a full transition matrix over a vocabulary of 50,000 tokens. They approximate it with neural network weights instead. Third, convergence conditions. A stationary distribution only exists if the chain is irreducible. Every state can reach every other state, and periodic, no deterministic cycles. If your chain violates either, the matrix multiplication will not converge. Always verify these properties before relying on the stationary distribution. So now, four things you know. One, a Markov chain models a system where the next state depends only on the current state. That is Markov property, memoryless, elegant, and powerful. Two, the transition matrix T encodes everything. Row I colon G equals to the probability of going from E to G. Every row sums to 1. Raise it to power n for n steps probabilities. Let it converge to the stationary distribution. 3. Google's PageRank is literally a Markov chain. The web is the graph, links are the transition, the stationary distribution of the random surfer is the page ranking. 4. LLMs generate tokens by sampling from a probability distribution at every step. A Markov style transition conditioned on all prior contexts via attention, but still a probabilistic transition at each generation step. And if this was useful, hit like and subscribe. Drop a comment. Which application surprised you most? Most people know autocomplete, but the RLHF conception to ChatGPT, that one changes how you think about AI. So for the next episode, Monte Carlo simulation, how you can estimate pi. Yes, the mathematical constant by throwing random dots, highly visual, highly practical. and used in finance, physics, and machine learning every single day. So, see you there.
By the way, if you are new to Python, I'm launching a Python formation. You can subscribe by filling the form in the description.